Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And in today's lecture, we will be seeing single phase, full wave controlled rectifier with resistive load. And here, there is a circuit diagram of single phase, fully controlled rectifier with R load. And here we are making use of 4 thyristors, that is T1, T2, T3 and T4. And as we all know, rectifier, the purpose of rectifier, it basically converts AC to DC. That means input is AC, which has got both positive half cycle as well as negative half cycle. And it converts AC to DC, that is alternating to direct current. And here, see, during the positive half cycle, that is during the positive half cycle of the input voltage, the polarities across the supply will be positive, negative, and here the polarities will be positive and negative. This is during the positive half cycle. And because of which, if you closely observe, the anode of thyristor 1 is positive, so obviously cathode will be negative. And since cathode of thyristor 2 is negative, anode will be positive. And because of these polarities, see, T1 as well as T2 are forward bias state. These two are in forward bias state, that is ready to conduct but not at conducting state. So at this instant, if we can provide the triggering pulse, at that instant thyristor T1 and T2 starts conducting. So here at this instant called alpha, we can provide the triggering pulse. Here, this is 0 and this is the instant called alpha, where I am providing the triggering pulse for thyristor 1 and 2, since these are forward bias, and T1 and T2 starts conducting at this instant called alpha, and it conducts till this instant called pi. And if you see, the output voltage is just similar to that of the input voltage. It is simply following the input voltage. That is because if you see, during the forward bias state, when T1 and T2 are conducting, see, T1 is acting as short circuit as soon as we have provided the triggering pulse. Thyristor T1 is forward biased as well as T2 is also forward biased. And here T3 and T4, since these are reverse bias, these two switches acts as off switch. T3 and T4 acts as off switch. So whatever the supply voltage, that is during the positive half cycle, whatever the supply voltage which we are actually providing, since T1 and T2 are short circuited, whatever the input voltage Vs will be appeared across the output voltage, that is V0. Here V0 is equal to Vs. Whatever the supply voltage which we are actually feeding will be appeared across the load. So that is the reason here our output voltage will be just similar to that of the input voltage which we are actually feeding. And so that is the reason it is simply following the supply voltage waveform. That is from alpha to pi. And the moment it reaches pi, what happens? Negative half cycle has been appeared. And because of which polarities will be during the negative half cycle, polarities will be negative, positive, and because of which again polarity is negative, positive, such that since anode of T1 is negative with respect to cathode, T1 is reverse biased. That means it acts as off switch, or we can also call it as open circuited. So what is happening now? See, anode of the thyristor T3 is positive with respect to cathode. That means T3 is forward biased. And similarly, if you see during the negative half cycle, since cathode of T4 is forward biased with respect to anode, even T4 is forward biased. So during the negative half cycle of the supply voltage, T3 and T4 are forward biased, such that T3 will be short circuited, if at all, if we can provide the triggering pulse at this instant called pi plus alpha. See, this is the triggering pulse which we need to provide during the negative half cycle, and due to which thyristor T3 and T4 will be forward biased, since T3 and T4 are forward biased, if we can provide the triggering pulse at this instant called pi plus alpha, T3 and T4 starts conducting current through the load. And here this is the output voltage because of T3 and T4 during the negative half cycle. You may ask me this question: why is it input voltage is alternating, which has got both positive half cycle as well as negative half cycle, and how we are achieving unidirectional output as an output? See, during negative half cycle, as I told you, T3 and T4 are forward bias, and we have provided a triggering pulse, and because of which T3 and T4 are now acting as on switch, which is conducting current through the load. See, when T3 and T4 are conducting, it is conducting the current through the load in this direction. This is the path during which the current flows in the negative half cycle. Even during negative half cycle, current through the load is flowing from positive to negative. That is the reason here we are achieving output voltage positive even during the negative half cycle of the supply voltage. That is, we are getting V0 is equal to Vs. And if you observe the same thing during the positive half cycle, this is the individual circuit diagram for positive half cycle, and during positive half cycle, see, this is the output voltage which we are actually getting during the positive half cycle. And if you see, during the positive half cycle, T1 and T2 is conducting a current through the load. And if you see, during the positive half cycle, T1 is conducting current through the load in this direction. See, this is T1 conducting current through the load, again T2 and back to supply. And if you see, the current direction through the load is, let us name this as A, B. So during the positive half cycle, current flow through the load is from A to B. Even during negative half cycle, current flow through the load is again from A to B. That is the reason here our output voltage is positive during positive half cycle as well as negative half cycle. That is how it is converting. Rectifier is converting AC to DC. That is how we are getting the DC output. So now, if you observe supply voltage in the positive half cycle, it is flowing in the upwards direction, and whereas in the negative half cycle, if you see, current flow through the load will be opposite to that of the first case. So that is the reason here supply has got both positive as well as negative, whereas current through the load is same in both the cases. Hope you understood the concept. And now again during the positive half cycle, polarities will be positive, negative, due to which again T1 and T2 will be forward bias, and at this instant we provide a triggering pulse. Because we are providing a triggering pulse during the forward bias condition of T1 and T2, here T1 and T2 starts conducting current right from 2 pi plus alpha to 3 pi. And here we are getting the output voltage because of T1 as well as T2. This is your output voltage for a single phase fully controlled rectifier. Coming to the output current. Output current, if you see, output current, it will be just similar to that of the output voltage. That is, output current is flowing through the load during the positive half cycle due to T1 and T2, and because of which current is flowing through the load from A to B, that is from alpha to pi. And at this instant called pi, since negative half cycle has been appeared, T1 and T2 is getting turned off. And again at this instant called pi plus alpha, since we are providing the triggering pulse, T3 and T4 came into the picture and it is conducting a current through the load. Again during the positive half cycle, T1 and T2 conducts current through the load. So this is about gate triggering pulses, output voltage as well as output current. How about voltage across the thyristor 1 as well as thyristor 2? If you see, voltage across the thyristor 1 and 2, see, voltage across the thyristor will be more when thyristor is under off condition, and during the on condition of the thyristor, the voltage which is appeared across the thyristor will be almost zero. It will be almost equal to that of the on-state voltage of voltage drop of the device, which is very less, which is almost equal to that of zero. So that is the reason, if you see, when thyristor T1 and T2 are in the off state, whatever the supply voltage which we are applying will be appeared across T1 and T2. So that is the reason the voltage which is appeared across T1 and T2 will be just similar to that of Vs. And this is during the off condition of T1 and T2. The moment when we are providing the triggering pulse, since T1 and T2 are turned on, because of which the on-state voltage drop of the device will be very less. It will be almost equal to zero. So now the output, the thyristor voltage across T1 and T2 will be almost zero. And again, at this instant, pi to pi plus alpha, since T1 and T2 are turned off, here we will be getting the output voltage waveform across thyristor 1 as well as thyristor 2. And again, at this instant, T3 and T4, since T1 and T2 are turned off, this will be a voltage across the thyristor 1 and 2. Since it is conducting from 2 pi plus alpha to 3 pi, this is 0. So the concept is, when the switch is short circuited, at that instant the voltage will be very less. It will be almost equal to 0. This is the thing. And if at all, if the thyristor is open circuited, in that case, whatever the supply voltage which we are applying will be appeared across the thyristor as thyristor voltage. That is what I have indicated over here. And now let us see the output voltage expression, average output voltage expression, where V naught average is equal to the general formula is 1 by T 0 to T V naught of omega T d omega T, where the time period is every similar cycle is repeating for pi over here. If you observe here, every similar cycle is appearing for pi. So that is the reason the total time period of the circuit is pi, where, and coming to the intervals, it is actually conducting from alpha to pi. So that will be a limits. Total time period is, it is every similar cycle is repeating for pi. So that is the reason here total time period is pi, and limits are, it is conducting from alpha to pi. Actual output voltage is present from alpha to pi, where V naught is equal to V maximum sine omega t, since this is a sinusoidal waveform. And here, in order to integrate this, let us take Vm constant out. We get Vm by pi, and integration of sine omega t is minus cos omega t. It is conducting from alpha to pi. In that case, applying the limits, we get minus cos pi, upper limit minus lower limit, minus of minus plus, we get plus cos alpha, which is equal to, finally, V naught average expression Vm by pi, since cos pi value is minus 1, minus of minus plus 1, 1 plus cos alpha. This is the average output voltage expression for single phase fully controlled rectifier with R load. Similarly, we will derive the V naught RMS expression. Here, V naught RMS general formula, it is given by 1 by T 0 to T V naught square of omega T d omega T, where here total time period is pi whole to the power of 1 by 2. This is the general formula in order to obtain V naught RMS. And here time period is pi, conducting from alpha to pi as explained. And here Vm square sine square omega T d omega T whole to the power of 1 by 2. And here constant, bringing it out, Vm square by pi, integration of sine square omega T. In order to be convenient, let me write the sine square as 1 minus cos 2 omega t by 2 integration, that is from alpha to pi. We get Vm square. Let me take this denominator out, 2 pi, and integration of 1 is omega t within the limits alpha to pi minus integration of sine to cos to omega t is sine to omega t by 2 within the limits alpha to pi whole to the power of 1 by 2. And here let me apply the whole to the power of 1 by 2. I get Vm, and this is root 2 pi, and inside let me apply the limits, upper limit minus lower limit, pi minus alpha minus sine 2 pi by 2, upper limit minus lower limit, minus of minus will be plus sine 2 alpha by 2 whole to the power of 1 by 2. In that case, we got V naught RMS is equal to Vm by root 2 pi, pi minus alpha, and this is sine 2 pi value is 0. Neglecting this, we get sine 2 alpha by 2 whole to the power of 1 by 2. So this is the V naught RMS expression for single phase fully controlled converter. And coming to the peak inverse voltage, if you see, peak inverse voltage is the maximum negative voltage which is applied across the thyristor during the off condition. So that is nothing but Vm. That is the reason here the formula for peak inverse voltage is equal to Vm. It is minus Vm, but we will consider only magnitude, that is Vm. Coming to the circuit turn-off time, because the definition itself says peak inverse voltage is the maximum negative voltage which is applied across the thyristor during the off condition. That is the reason it is Vm. Coming to the circuit turn-off time. Circuit turn-off time is the time during which the thyristor is off. That is from, if you see, it is off from 2 pi to pi plus alpha. So we get circuit turn-off time is equal to 2 pi minus pi plus alpha. It is off from 2 pi to pi. Circuit turn-off time 2 pi minus pi by omega. That means we get pi by omega is the circuit turn-off time for single phase fully controlled rectifier with resistive load. So in the coming up lecture, we will be seeing single phase fully controlled rectifier with resistive RL load. Thank you.